All right, let's go ahead and talk about polar molecules. And so we've talked about polar bonds, and polar bonds occurs in covalent bonds where there is an uneven sharing of electrons. And the reason why that happens is because one atom has a greater electronegativity than another one. And so because it has a greater electronegativity, that means it has a greater pull on those shared electrons, and so it pulls those electrons closer to itself. Now those electrons are still being shared between the two atoms, it's just the more electronegative atom is going to be pulling it closer to itself, making that atom partially negative. Now again, it's not a full negative, because if it were a full negative, that is what an ionic bond is. Now the other atom, which has the negative electrons being pulled away from it, again, it's still sharing those electrons, it's still participating in the covalent bond, it's just that those electrons are being pulled away from it, and that atom becomes partially positive. And again, it's a partial positive and not a full positive, because if it were a full positive, that is what an ionic bond is. And so again, they're sharing electrons, but it's an uneven sharing of electrons. What ends up happening is you have a partial positive end and a partial negative end, which creates a dipole. Now this same exact thing can happen with entire molecules. And so you can have polar molecules where one end of the molecule is negative and the other end is positive. And so let's go ahead and talk about that. So a polar molecule is something that will have a net dipole. And again, a dipole is created by equal and opposite charges separated by a certain distance. And so if you take a look, this is actually an example of a polar molecule. This is a water molecule, and notice how the electronegativities are written on there. The hydrogen is 2.2, the oxygen is 3.44. That's a difference that's 1.2, which is greater than the 0.4 difference that you need to have a polar bond. And so you'll see that there's two polar bonds. Each bond is a polar bond, each oxygen-hydrogen bond. Now, the two dipoles are being pulled towards oxygen, and what ends up happening is the side of oxygen becomes partially negative. Now, it's not a full negative, it's a partial negative. Now, the hydrogen side becomes partially positive, and so the molecule itself is a polar molecule. Now, for a molecule to be polar, there's two things that need to happen. It needs to have polar bonds. Okay, we talked about how to determine that. And it needs to have an asymmetrical shape. And so we're going to talk about that here in a moment, what that means. But essentially, it's got to be a shape that allows for the dipoles to create an overall dipole. You can have a situation where a molecule has polar bonds, but the dipoles cancel each other out to where the molecule itself is not polar. So let's go ahead and take a look at two examples of this. Notice how the carbon dioxide, the CO2, notice how that is a linear shape. That's a linear shape. And what ends up happening is there are polar bonds between the carbon and the oxygen. The polar bond creates a dipole going this way to one oxygen, but then it creates a dipole going the other way as well. And so notice how those dipoles actually cancel each other out. They sort of go in exactly the opposite direction. Now look at the SO2. Notice how it's literally the same thing. The sulfur and oxygen create a polar bond, except notice what the shape is. The shape is different. It's not a linear shape, it's a bent shape. And why is it bent? It's bent because the lone pairs repel the bonded pairs. So the lone pair that's on sulfur repels the bonded pair, making the bent shape. And so you have these sort of dipoles that are going like this, and I'm going to bend upwards, it's easier. But then what happens if they're bent upwards, they're actually now sort of going in a similar direction to where there's an overall dipole going in one direction. So they're no longer canceling themselves out. And the way I like to think about it is, imagine you have a cart, and one person's pulling on the cart this way and the other one's pulling on the cart this way. The cart won't go anywhere, and we're assuming the people are equal strength. But imagine you have a cart, and in the second situation, the S is the cart, and you have one person pulling this way and one person pulling that way. They're not pulling in the same direction, but it does cause the cart to move in a certain direction. And so that's sort of how you want to think about it. do the dipoles go in a direction where they're not necessarily canceling each other out, but actually adding on each other? And in the second situation, they are. So carbon dioxide is a non-polar molecule, but SO2, the sulfur dioxide, is a polar molecule because of that asymmetrical shape. All right, so let's go ahead and take a look. Here's 3 examples of polar molecules and then 2 examples of non-polar molecules. And you can see the BF3, the dipoles kind of all go in a direction where they do cancel each other out. You'll see that the NH3, they don't do that because the nitrogen has lone pairs that push the bonds down, and so instead of the bonds all going in on each other like this, they're actually kind of going upwards, and so they do have a common direction in which the dipoles are going. And you'll see that in the CCl4, the dipoles are all canceling each other out there because again, they're all going in a direction to where if you add it all up, they end up canceling each other out. Now, what I want to notice is, or I want you to point out, or I want you to notice is the C3Cl, and it's the upper right molecule. Notice how that shape is not an asymmetrical shape, but that is a polar molecule. And the reason why that is because it has different atoms attached to the central atom. If there's different atoms attached to the central atom and there's a polar bond, that actually will create a polar molecule because there's not a dipole that's canceling out that one dipole. So we'll talk about that more in the guided practice. All right, so lone pairs do affect molecular polarity. And essentially, if a molecule has polar bonds and the central atom has lone pairs, that will be a polar molecule. And that's because the lone pairs are going to push the bonded pairs in a way where it's going to create an overall dipole. So again, notice how in the SO2, how the lone pair pushes the bonded pairs down and allows for an overall polar molecule. And you can see the same thing in the NH3. Now, polarity affects the intermolecular forces of attraction. That's something we have not talked about yet. We have not talked about intermolecular forces. That's actually going to be the last thing we learn in this unit. But essentially what intermolecular forces are, they're the force of attraction between molecules. And so molecules actually can be attracted to each other. In fact, they are. They all have some sort of attraction, and some of them are more attracted than others. And so what I want to point out is notice the water molecules, the H2O. So we have each water molecule, which is a polar molecule. And again, a polar molecule has a negative end and a positive end to it. Well, it turns out that if you have 2 molecules that are polar, the negative end of one molecule will be kind of attracted to the positive end of another. And so notice the red dots that occurs between the hydrogen and the oxygen. That is an intermolecular force. That is a force of attraction between molecules. Now, some molecules have a larger intermolecular force than others, and that's what we're going to learn next class period. But that's going to be something that's different than the intramolecular force, which covalent bonds are intramolecular force. And so this is kind of a sample of what we'll be learning next class period. So as we're thinking about polar molecules, we want to think of in the future about how we're going to learn how polar molecules are attracted to each other, how non-polar molecules have a smaller attraction.